Electricity generation, question 1. A pumped storage power station has an upper reservoir with an area of 13,000 square meters and a depth of 22 meters. The water falls a height of 270 meters to the turbines and takes 2 hours to go from full to empty. Part A. Calculate the mass of water the reservoir can hold, given that the density of water is 1000 kilograms per cubic meter. Well, mass is equal to density times volume. The density we're given here of 1000 kilograms per cubic meter. The volume will be the area of 13,000 square meters times the height of 22 meters, giving a mass of 2.86 times 10 to the 8 kilograms of water. Part B. Calculate the potential energy of the water. Well, the change in potential energy of an object is given by its mass multiplied by the gravitational field strength multiplied by the change in height. In this case, the mass of the water we found previously at 2.86 times 10 to the 8 kilograms. The gravitational field strength 9.81 newtons per kilogram, and the change in height as it drops to the turbines 270 meters, which was given in the question here, giving a potential energy of the water of 7.6 times 10 to the 11 joules. Part C. Calculate the maximum average power output of the station. Well, power is equal to work done over time taken, or energy transferred over time taken. The energy we have available is the 7.6 times 10 to the 11 joules stored in our water, and the time taken is the 2 hours given in the question to go from full to empty. So the energy transferred, 7.6 times 10 to the 11, over the time taken, 2 lots of 60 minutes, each of 60 seconds, giving an average power of 1.06 times 10 to the 8 watts, or 106 megawatts. Part D. If the station has an output of 100 megawatts, calculate the efficiency of the generation process. Well, efficiency is equal to useful output power divided by input power. The useful output power is our 100 megawatts, the input power 106 megawatts. So the efficiency is 100 over 106, which is 0.94, or we could say 94%. Part E. The water is pumped up over an 8-hour period by 6 6-megawatt pumps. Calculate the energy taken to return the water. Well, energy transferred is equal to power multiplied by time taken. The power is 6 pumps, each of 6 megawatts, multiplied by 8 hours, each of 60 minutes duration, each of which is 60 seconds. This gets our time into seconds, giving a energy transferred of 1.04 times 10 to the 12 joules. Part F. Calculate the efficiency of one complete generation cycle. Well, here I'm going to take efficiency as useful output energy divided by input energy. Previously we took it as useful output power divided by input power, but as long as we have either energy or power top and bottom, the equation will give the same answer. The useful output energy, well, it's 100 megawatts, this gives the 100 megawatts, for 2 hours, which is 2 times 60 into minutes times 60 into seconds, divided by the input energy we found up here as 1.04 times 10 to the 12 joules. So this is the energy we get out of the generators, this is the energy we put in to the pumps, giving an efficiency overall of 0.69 or 69%. Finally, part G. If pumped storage power stations produce less electricity than they take in, why are they useful? Well, electricity is very difficult to store. We can store electricity in batteries, but they are incredibly inefficient. Pumped storage systems can provide electricity quickly when needed. They can go to maximum production in a matter of a few seconds. They can return the water at low peak times when electricity is cheaper. So basically they provide electricity when it's needed and will take in electricity when supply is greater than demand.